Now, the dispersion, or you notice just now, it starts from concentrated and it starts to be dispersed laterally and vertically. We don't think of the dispersion horizontally because as it moves on, it does have some horizontal distribution, but then it will mostly be of the same concentration. Mostly the concentration that's in the middle of the plume will be dispersed. Okay, it carries downwind, but then as it goes downwind, it becomes larger this side and also becomes taller this side. So the concentration in the middle gets spread out here and spread out here as it moves downwards. But we think of the concentration in the middle to be the same. Now, what makes it disperse laterally and vertically? What causes it to spread out? By two different categories. There's the horizontal transport, like I mentioned, and the vertical transport. So the horizontal transport is determined by changing of wind direction and terrain. I think that makes sense, right? So if the wind changes and the plume moves with it, of course the horizontal spread will be larger. Vertical transport is very important because this is the capping of pollution. Because if vertical transport is very large, then the impact of a stack to the downwind concentration will be much lower because it gets spread out over a larger vertical distance. We are more concerned with the vertical transport than the horizontal transport because of its capability to disperse is higher than the horizontal transport. Now, this vertical transport is determined by meteorology, or specifically the temperature profile of the atmosphere. I think you've maybe been exposed to this. How does the temperature change with height? Whether it decreases with height or is it increased with height? This change in temperature with height determines the stability or the vertical transport of the atmosphere. Number two, vertical transport also depends on, not also depends on temperature profile. It is important because this vertical transport is the upper limit. So if there is limitless vertical transport, there is no upper limit, so it can be dispersed even more, and thus quickly reducing the concentration of pollutants in the air. So this is the normal distribution, like I mentioned just now, where right in the middle is high concentration, somewhere at the edge is low concentration. So from here to here is one standard deviation. You've heard of this term before, right? Well, in the middle is the mean. So this area is 75% of the curve. So if it's 2 standard deviation, it's about 68%. Sorry, I didn't see that. So somewhere here, 1 standard deviation from here to here is 68% of the area beneath the curve. If 2 standard deviation is 95% of the area beneath the curve, at 99.7% is at 3 standard deviation area of the curve. So you notice how we classify the dispersion is through its standard deviation, how wide it is. So I'm going to show you this video. Let me close this for a while. Okay, you don't have to listen to it because it's not that clear anyway, so I'll just narrate it for you. So here we have a tracer gas. It's not really a stack. It's just a pole with a simulated release of pollution at the end, and it shows the dispersion, the vertical dispersion of this pollutant as it travels downwind. You notice the vertical dispersion of that. Now, this way of dispersion, or this magnitude of this vigorous mixing in the atmosphere, is because of the vertical transport due to the convective condition of the atmosphere at this point. That means it is unstable. It is under an unstable condition, which causes it to be dispersed this way. And this quickly reduces the concentration of the middle point of the plume. Of course, what you saw just now is an idealized plume where you see it to be like that. But if you were to average all of the points of all this, you notice that, and then draw a line, you notice that it would look like the Gaussian dispersion. But of course, real time, it doesn't. Real time, it does fluctuate by a lot. But once you average it, it approaches that Gaussian dispersion. So, Gaussian distribution. Let's see. How come? Now, this is horizontal dispersion. Let's say there's a change in wind direction. Notice before that it was in that way, and then it's in the other way. Okay, this what you see so far is this is still unstable atmosphere, where you see the plume goes up and down quite vigorously or quite quickly. While this is if it's under stable condition, or where the temperature profile is for the stable condition. You notice that the plume moves downwind, it doesn't disperse that much. Now, it might be safe for people down here, but then let's say if this were to drop down, at one point, it will drop down at a higher concentration compared to if it dispersed right in the beginning. So you can see how markedly different they are between these types of the conditions of the atmosphere. So just to summarize, like say this one, unstable condition or convective condition, while this one is stable condition or it's still called stable condition. It's not there's no word for it. Like before, unstable is related to convective condition, while this one is just stable condition. Now, just to give you a preview of what it means by stable condition and unstable condition, I'll just show you the temperature profile. If this is height, and this is temperature. Unstable condition is where the temperature at the bottom is higher than the temperature somewhere at the top. This is unstable condition or convective condition. While if it's cold at the bottom but hot at the top, is a stable condition. Two main groups, but then of course there are ranges within these two main groups. There's the very stable condition, there's the weakly stable condition, there's the very unstable condition, there's the weakly stable condition, and so on. And you can see the effects on the plume from there.